Okay, good afternoon, everyone. So today we are going to finish off the quadrature topic with Gaussian quadrature. Okay, so if you remember in the Newton-Cotes rules or the interpolation rules, at first you choose the point x1 up to xm equally spaced, yeah, or you choose it in advance. And then after that, you find the weights, right? By integral the Lagrange polynomials. And then the rules will be exact for polynomials of degree m. And we say that the degree of precision is at least m. Okay, so this is a theorem. But then Gauss, okay, so Carl Friedrich Gauss is a German mathematician who lives in the 19th century. He said that, well, I can do better than this. Yeah. So I say that he said that if you choose the points and the weights at the same time, okay, so you have more freedom, right? You choose the weights and the points at the same time. Then you can make the degree of precision is higher. Yeah. So with m points, Gauss can design a quadrature that has degree of precision is 2m minus 1. Yeah. And so we just focus on the intervals minus 1 to 1. But then after that, you can make a transformation to make any integrals from the interval a to b maps into minus 1 to 1. Okay. So we will say the idea. So the idea is, suppose you have 2 points. Okay, so 2 points. And you want the degree of precision is 3. So 2m minus 1 is 3. Yeah. So remember, with Newton rules, at most you can have degree of precision is only 2, right? Or even less, maybe 1. But this one, the degree of precision can go to 3. And how do you do that? Well, you have to solve the equation of 4 nonlinear equations. Okay. So the first one, just say that, okay, integral of the function 1 is exactly equal the quadrature applied to the function 1, right? Because 1 times w1 plus 1 times w2 is the quadrature applied to the function 1. So it has to be equal the integral from minus 1 to 1. And then, like if you integral the function x from minus 1 to 1, then it will equal the quadrature applied to the function x, right? So you have w1 x1 is just the weights, the first weight multiplied with the f evaluated at the first point x1, and so on. For x squared, then the integral has to be exact to the quadrature applied to x squared and up to x cubed, right? Because you stop at x cubed, yeah, you want the quadrature to be the same as the integral. And you see, because it's nonlinear, and remember, you can solve nonlinear equations, right? At least numerically. So you studied already. So in this case, the solution is just the weights is just equal 1. W1, W2 just equal 1. You can say that 1 plus 1 equal 2. Integral of this one is just equal 2. So that's correct, yeah. And then x1 and x2 are opposite sign and equal plus or minus 1 over square root 3. And you put it in here, you can check. If I put in here, then I got a 0 here, then integral on the left equals 0. So it's correct, yeah. So the third equation, you put it in here, you got 1/3, 1/3. So 2/3. So this integral is 2/3, right? And the last one, you put it in, you got 0 on the left, on the right, 0 as well. So it's a solution. So then you see, with 2 points, you can achieve degree of precision is 3. And so this one can be put in this format. So integral from minus 1 to 1 is just approximately by f of minus 1 over root 3 plus f of 1 over root 3. So the weights are 1. And then we don't have to prove this, but it can be shown that, I mean, the errors. So this is the errors, yeah. Integral of f is the exact integrals minus the quadrature. It just equal the fourth derivative at some point over 135. So we are not going to prove it. And I think I leave it to you to check that if you use 2-point Gauss-Legendre to, well, some people call this a Gauss-Legendre rules, okay, but it's a Gaussian rules. If you use only 2 points, you evaluate this integrals, then it's the same as you use, you know, trapezoidal rules with how many points here? So 4 points, yeah. So because h is 1/2, 4 points, or Simpson rules with 2 points, yeah. So you can check that. So now what happened if you want an n-point Gauss-Legendre rules? Okay, so we are not going into details, but essentially you can design an n-point Gauss-Legendre rules by solving a system of nonlinear equations, yeah. And we can show that the errors, okay, will be of this form. So you see n here is 1 over n factorials. So it's going down very fast. You see, so this one is, you know, if you use Stirling formula, you can approximate the factorials by, you know, some exponential function, and you can show that this one going down like a constant over 4 to the n. So it go down very fast, yeah. So we just knows that. And you see, this one is the case when you have n equal 2 or 3 points or 4 points. And even it look like this, but you can write down in terms of a more beautiful fractions like this. So 2 points, and you have plus and minus 1 over √3. Weight is 1, and 3 points plus or minus square root 3 over 5. And the middle just equals 0, and the weight here, and 4, and so on. So based on that, you know, you have to solve it numerically, because you see the this one is still write down in a nice form, but more than that, they're just numerical values. And then, you know, suppose you have integrals from a to b, then you can make the change of variable like this, right? To transform the integral from a to b into integral from -1 to 1. Yeah, so this one is first year calculus. Then you replace this integral from -1 to 1 by the weight, yeah, by the weights and the quadrature points from -1 to 1. Okay, so now this one is the one that you saw in the lab. If you remember in the lab, maybe last week, we saw that if you put a square root in the function, sorry, in the integrand, yeah. So in this case, I just integral square root x from 0 to 1. Then I put a trapezoidal rules. I measure the order of the errors. It's 1.3, 1.49, so about 1.5, right? And I put the Simpson rules, yeah. I measure the errors, then I measure the order of convergence, yeah, of the errors. I got only 1.5. So what is the theoretical results? So what is the theoretical results for trapezoidal rules and Simpson rules? Anyone remember? So what do you expect the order here? What do you expect the order for trapezoidal rules? Anyone? So just a few slides ago, I mean, if you remember, So if we go back to a few slides, yeah, the the trapezoidal rules. Yeah, so this is the row is the order of the errors, yeah. So suppose the errors is CH to the row. Then trapezoidal rules, the theory say that the error should be of order h square. Okay, so order should be h square. So the order of convergence should be 2. And Simpson rules, yeah, the order of the errors going down like h to the 4, yeah. So here now this is the case that you see the order is 4 here for Simpson rules and order is 2 for trapezoidal rules. But when I put in the square root, then now I got only order 1.5 for trapezoidal rules and 1.5 for Simpson rules. So what is going on? Anyone? So why we get this? Why we get that lower order for this function? So my MATLAB is wrong, or the theory is wrong, or the table is wrong. So this is important. So this one is for the project. You have to write out some errors table. You have to print out some error table, and you compute the order of conversion as well. Okay, so for Runge-Kutta method, you should get order 4. And if you get order 1, then you claim that MATLAB is wrong, lecture note is wrong, lecturer is wrong, everything is wrong except you. Okay. So what is going on here? Anyone? So what is going on? So why I got only 1.5 here instead of 2? So maybe I let you look at the theory again, yeah? So what does the theory say? Say maybe for Simpson rules, yeah? So what is the error say? Well, it say that the errors is of order 4, right? However, you need the 4th derivatives of the function, right? For this to make sense, right? Otherwise, it doesn't make sense. I mean, similarly here, you need the 2nd derivative, of the function, for the errors to make sense, yeah? And if you look at the integrand here, the integrand is square root x. So what is the derivative? So what is the derivative of square root x? Anyone? Yes. So now what happened when x go to 0? What happened when x go to 0? Blows up, right? Because I mean 1 over square root x go to 0 just blows up. So it's not the derivative. The first derivative is not continuous on the intervals. Okay, so therefore you cannot apply this theorem. So this theorem assumes that the function have to be differentiable, I mean, at least on this one is fourth type derivative, yeah. And this one, the errors, the second derivative is required for all the points from A to B. Yeah, so this one essentially, if it doesn't satisfy the condition, then you cannot apply this theorem, right? So that is important. Okay, when you look at the theorem, you have to look for the assumption. You see, so this one is the theorem say that if f is C2, it means that the second derivative is continuous on the intervals, closed interval, A comma B. Yeah. So the square root x doesn't satisfy this condition. So therefore this doesn't apply. So therefore, you see, if you take the function is square root x, you don't expect you got a convergence according to the theory. I mean, when you integrate from 0 to 1, because the derivative, the first derivative blows up already. Okay, and second derivative doesn't exist, so you need second derivative for trapezoidal rules and fourth derivative for Simpson rules. So then you have order convergence 4. Okay, so in this case, then you need to change the variable, say x to y square. Okay, and then the integral will become a integral y square dy. And then you see this function, it has derivative, second derivative, fourth derivative, and so on. Or sometimes you have a integrand like this. You can see that, you know, I mean, if you plot it, you will see there's a cups at 1/4, yeah. So not differentiable at 1/4. And then you have to split the integrals into 2 separate integrals, and it will be okay, yeah. But now you got a square root as well, and then be careful, you know, like you have to transform square root into like y square like this. Okay, or you can have a oscillate integral. So this one is highly oscillating integrals, you know, sine 50x, so up and down very quick. So then you have to, you see there's a plot here, then you have to use a lot of subintervals. So this is the first integrand, the second integrand, the third one. Okay, so in MATLAB there is a function quad. So you have to give a function handle of an anonymous function and integral intervals from A to B. So then it will use Simpson rules. You know, there's a few other functions, but I just let you look it up. Okay, so MATLAB have implemented Gaussian rules, Simpson rules, and a few other rules as well. Okay, so please check. So that is everything about quadrature. So any question about this? Otherwise, we move to the last topic. Yeah, so the last topic will be on initial value problem. So initial value problem, let me go back to the very first slide. So so we so in this topic we look at a few methods. So the first method will be called single step methods. Yeah, so single step methods we have Euler's methods and Runge-Kutta methods. And then single step is, you see that you will look up, you know, like just a previous step. And the multi-steps is you will look up like more than one step. Okay, so then we will look at the system of ordinary differential equations. So this one is like the project you are doing. Okay, and then how you use MATLAB to solve it. So essentially the project cover like half of the topics here. So the initial value problem. So this one is one simple example, okay, of initial value problems. So suppose, okay, this one is Newton law as well. So Newton discovered this law, yeah. So he say that suppose you have two objects, yeah, and then you let the heat transfer from one object to another, yeah. So essentially, suppose you have like the human body and you have the temperature of surrounding medium like in your room, then your body is cooling down according to this equation, so the rate of change of the temperature is proportionally to the difference of the temperature. Okay, so this is the ODE. So on the left, you see the different derivatives for first order, yeah. Or you drop something, say from the top of the library building, okay, then it accelerates down to the ground, yeah, and then it will follow this Newton law as well. So this one is just the acceleration equal to minus the gravity acceleration, gravitational acceleration, okay. And see, you have to give the initial point. So suppose you stand in front of the balcony in the library in level, say level 10, then S0 is like maybe like 20 meters or something, and you throw something down, right? So then you have some initial velocities, okay? Then it's going down according to this equation. Or you see this one is in the project, yeah? So you saw that this one is a simple models for the atmospheric convection, okay? So proposed by Lorentz in 1963. And see, now it's a system, okay, of three differential equations. So X, Y, Z is just like the state of the system, yeah, and rho, sigma, and beta are some parameters, okay. So when you plot it, it will show you, the trajectory, because X, Y, and Z can be plotted in space, right? Because given X, Y, and Z is a triple coordinates, right? So you can plot it in 3D space. And I will show you this video, but maybe I will put a link into Moodle. You can watch this video, or you can look it up, Lorentz attractor. So when you solve the solution, when you solve the system, the Lorentz system, right? So the solution will track in space a set like Lorentz attractor. So we don't have time to play the video now, but I will post a link and you can play on it. And so now before we do the numerical calculation, let's study a brief, theory about existence of the solution. So existence and uniqueness, yeah, because otherwise our numerical solution will not make sense. So the theory say that, okay, suppose, well, maybe first we define the problem first, yeah. So the problem has the form, dy over dt is just a derivative with respect to, say, time on the left, and on the right you have a function that depends on time and depends on y as well, and you have some initial value. So at time equals 0, this is given, like, in the acceleration problem, I mean in the dropping down something, then you have an initial velocity, you have an initial coordinates, yeah. And now we have some assumption this is what they call a Lipschitz assumption. So the function doesn't, well, I mean, suppose you take 2 points, y1 and y2, right? And you apply the value of the function, then the distance doesn't go very far compared with the original distance of y1 and y2. Question? When you plot it, it doesn't look that cool. Okay, that's a good point. Did you have a correct solution? Well, first, you have to check whether you got a correct solution, and you plot it, and you will see that the Lorentz attractor look, very nice. It's very famous. Okay, so we go back to the theory a bit. Yeah, so the theory, so this is just assumption. Yeah, on the function f. Yeah, and then you have to assume that the function is bounded as well, right, on some region, and assume that the function is continuous in 2 variables. Then so a special case is if the function is continuous differentiable, right? Then the derivative, the partial derivative is bounded, and then it's Lipschitz. Yeah. So now the theorem say that, okay, so suppose you have on the nice assumption, function continuous, bounded, Lipschitz, then the theory just say that, okay, there exists a point t star and a function y that satisfy the initial value problem. Essentially, you can solve it, okay? Otherwise, you solve it numerically, and people say that, oh, but this system doesn't have a solution, so your numerical solution doesn't make any sense, something like that, okay? So an example, so simple example. So suppose I have dy over dt equal 1 plus y squared, okay? And y0 equal 1. So now the exact solution of this one will be tan of t plus pi over 4. Yeah. So how do you find that solution? So how do you verify that the exact solution is this? Yes, you can differentiate directly. Yeah. So if you take tan, yeah, then the derivative of this tan is just 1 over secant square, right? Okay, so 1 over secant square. Yeah. Sorry, 1 over cosine square, or just secant square. Yeah. And secant square is just 1 plus tan square. Yeah. By trigonometric identity. So therefore you get exactly the ODE. But you need to check that the initial condition is correct as well. You put in t equals 0. So t equals 0, tan of pi over 4, just 1. So that's correct. Yeah. So this function is continuous from 0 to close to pi over 4. But when it approaches t equal pi over 4, then you got tan pi over 2 just blows up, right? So you remember the plot of tan, you can plot it. Yeah. So now we're looking at the numerical solution. So now we divide the, maybe this one I should draw a picture so it make more sense. Yeah. So we draw pictures. Yeah. So suppose now the function is not known. Yeah. So you got dy over dt equal f of dy, right? So now we try to solve it numerically. So you have, so suppose you got t0 here, t0 equals 0, right? And then you got t1 here, yeah? And you got t2 here, right? And so on up to capital Tn. Yeah. And to make life simple, I just make all the intervals equally spaced. So the width is just h, yeah. Okay, and now remember y0 is given, so y0 is here. So y0 is here. Okay, so Tn, so T1 is just equal h, T2 equal 2h. Okay, and so on. So you got Tn is just equal nh. Okay, so now numerically y0 is given, and you try to find y1, right? And y2 and y3 and so on numerically. Okay, so suppose you can find those points. So this one is given, right? So y0 is given. So suppose you can find y1, y2, y3. Yeah. Then how do you construct the whole solution? So let example, there's a formula to find y1, y2, y3. Then how do you find the full solution? So how do you find the full solution? Somebody say something. Yeah, so solution is just a curve that connect y0, y1, y2, y3. Exactly. And remember that process, we studied that already. So the process that connect on the points is what? We studied already in chapter 4. So what is the process to connect on those points? Interpolation, yes, interpolation, right? So you see, once you have a collection of those points, you can use interpolation to construct the solution everywhere. Okay, but in this topic, I mean, in this chapter, we just focus how to construct the sequence y0, y1, y2, and y3. Yeah, and so one simple way, okay, is suppose I have dy over dt is f of ty, right? This one is the ODE, right? So now if I integral from t0 to t1, okay, so integral from t0 to t1, so dt, right? So this one is dt. Then I got y t1 minus y t0 equal integral of f, or maybe I should change the variable into s, y dt, right? So from t0 to t1, right? Yeah. ds, root point, yeah, should be ds. Yeah. And now y t1 equal y t0 plus integral from t0 to t1 f of s, y of s, ds, right? Yeah. So now remember, so now this is just an integral, right? And how do I approximate the integral? So remember, this is just an integral under the curve, say, of function f from t0 to t1. Yeah. So how do I approximate the integrals? Quadrature. You study quadrature in the previous chapter, right? So now you just need to put in a quadrature and you get a solution for the ODE. Yeah. So now suppose I put in, say, rectangular rules. Okay. So suppose I make the integral is just exactly the area of the rectangle. Yeah. Then what I have is Now I have YT1. I no longer have an equality, but I have approximately y, okay, y0, yt0 is given, it's just equal y0, yeah, plus, and now the width is just h, right? Because remember we assume from t0 to t1 it's just h, and then you multiply with the value at t0, y t0, right? And now I label this one is y1. So y1 is y0 plus hf t0 y0. Okay, and then y2 is just y1 plus hf t1 y1, and so on. So yn plus 1 is just yn plus hf tn yn. Okay, so this one is the Euler method. So Euler is the first mathematician. I think he's originally is from Swiss. He's a Swiss. I think he's originally is a Swiss, and then later in life he moved to Russia. You know, so he discovered this formula in 1760 or something like that. Okay, so this one is named after him as Euler method. So, but now it looks simple for you, but you see, 300 years ago, you know, I mean, it's complicated. Remember, at that time there was no computers, no MATLAB, nothing, you know. So yes, Euler name is everywhere. I agree. Euler, Newton, Gauss. Yeah, MATLAB was written in maybe 1984 or something, you know. So go back to the slide, yeah. So I just explained to you what Euler discovered 300 years ago. So Euler method is here. So essentially, I just wrote down, yeah. So in 1768, okay. So this is the formula. Okay, and then, you know, I mean, you can interpret this by Taylor polynomial, right? So before it's like you use quadrature, but you can interpret by Taylor polynomial. So you expand y around t0, and you just take the linear terms, yeah, and then you use this to define y1. Just the same way to get the formula. So now let's take a very simple initial value problems. Okay, so y prime equal t plus y. So if you remember your first year calculus, you can solve this one exactly, and you get the true solution. Okay, so if you remember first year calculus, you have to write down a characteristic equation, and you know, you solve a homogeneous equation, and then after that you try to find a particular solution. Okay, but you know, we don't focus on that, so it's just given to us. And now if you put in Euler formula, then you can see that, okay, so now I just take the step size equals 0.1, yeah, and then you can compute the sequence. Y0 is 1, y1 is 1.1, y2 is 1.22, y3, so on. You can write a MATLAB script for this. Okay, so this one is more or less the first part of the project. Yeah, you just write out the Euler method, and you see the errors. Initially, it becomes 0, right? But the errors get a bit bigger. So 0.01, 0.02, 0.03. So get bigger and bigger, right? And now suppose you use Euler method okay, to solve this problem. So again, I just assume that you know how to find the exact solution. Yeah. So exact solution in this case is just t over 1 plus t squared. And now we observe the errors. So the errors here is defined to be the exact value of the solution minus the numerical solution. Okay, but then now we take the maximal over on the points. Okay, on the points in the partition. So here I have, say, h equals 0.5. Then I have t equals 0, t equals 0.5, and t equals 1. Okay, then I measure the errors. So the errors is equals 0 initially and 0.1, 0.15. So the maximal is 0.15. And now I do the same, but now I reduce the step size. Okay. So you see the same ideas in the project here. I mean, in the project, you have to reduce the step size. You have to measure the errors. And you see here, you take the maximal over on the intervals. Yeah. And it's 0.0545. Yeah. And you reduce the step size by half. Okay, so now becomes 0.1. And you compute the errors as well. So the errors is not always biggest at the final point, right? Because look at this one, you see, 0.0259 is about 0.7, yeah? So, but now what is the, and if you reduce the errors by half, you know, sorry, reduce the step size by half, then you get the errors is 0.01. So what is the order? What is the order of convergence? If you look at this sequence. So what is the order of convergence? You see, so the errors, so the step size reduced by half, right? Every time the step size reduced by half, yeah. So what happened to the errors? So 15, maybe not very clear, but say here from here 0.05, reduced to 0.02, reduced to 0.01. Order 1, yes, order 1, because you see, yes, order 1, yeah. So the step size decreased by half, errors decrease roughly by half, and so it means that the order of convergence is just 1. Okay, so if you do the project for the Euler part, you expect order 1 convergence as well. So now that is a numeric observation. So now we try to prove it for general case. Okay, so now before we prove it, let's see. There is a concept called local truncation errors. Okay, so we will use this to prove why the order of convergence is 1, Euler method. So in the project, you don't have to prove it. Okay, so in the project, I just ask you to write a program, produce the numbers, observe from the numbers, and deduce the order of convergence. So then you don't have to prove it. But this one is just for education. So we need to know why it's true, you know. So first, we define local truncation errors. So local truncation errors is defined with this quantity. And if you look at this quantity, it's the difference between the numerical derivative, right? Because when h go to 0, this one go to the exact derivative of y, right? So when h go to 0, this one is just go to y prime, and y prime minus f is equal 0, right? Because that's ODE. So this local truncation errors will go to 0, right? When h go to 0. So somehow just try to measure how good your numerical derivative is, yeah? So we call it local truncation errors. And now, you know, if you put t equal tn, yeah, then you got the errors, the local truncation errors at the end. Yeah, and you cross multiply you know, h with capital T, then you got this equation. Okay, so we leave it here. Yeah, so y, so maybe let me write that first. Yeah, and then we can show you like the proof. Let make a very rough proof first. Yeah, and now you gotta so local truncation errors is defined to be this y of t plus h minus y of t over h minus f of t and y, right? So t comma y, yeah. So if you put in tn, okay, then this one become y of tn plus h minus y of tn over h minus f of tn yn. Sorry, just y of tn, yeah. So y of tn. Okay, and this one, so tn plus h is just y of tn plus 1, right? So, and then you multiply by h. So you multiply by h, you got h t capital T tn y at tn plus 1, yeah, minus y tn, okay, minus h f of tn y tn, right? And now I just rearrange. I want to rearrange it a bit, yeah. So if I rearrange it, then I got y. What I move everything with respect to tn to the left and rearrange it. So you can see that, or maybe move y tn plus 1 to the left, yeah. So I move it here. Then you rearrange it. So you got h capital T n minus no, become a plus, yeah, y tn plus h f tn y tn. Okay, so now what do I want to do? So far so good, right? So now what is the well, so first I want to, so we just remember this equation, yeah. So remember this equation. Okay. And now let me focus on the local truncation errors. So local truncation errors, yeah, in general is so local truncation errors. Okay, so this one for Euler method, local truncation errors is just of order h, yeah. So this is the theorem here. So this one is local truncation errors at any point t, okay, is just of order h, right, and plus some terms of order h square. Okay, so how do I prove it? Well, because I just used Taylor theorem. So let's see, how do I get Taylor theorem to show this? So maybe a bit too fast here, yeah. So let me write down the proof of. So now first I want to show that, okay. So now first we want to show that T, I mean the local truncation errors is, so we will show that T is just 1/2 y double prime th plus OH squared. Okay, so how do we prove it? Well, first we use Taylor expansion. Okay, so Taylor expansion. So remember Taylor expansion of the function y, yeah? At t plus h will equal y at t plus y prime t times h plus y double prime t over 2h squared, yeah, plus something higher order. So I don't worry about higher order terms now, yeah. And now if I take, I mean rearrange it, so I got y t plus h minus y t, okay, and minus y prime h, then I got y double prime t over 2 h squared plus oh cubed, right? And now I divide everything by h. So if I divide everything by h, then I got this y t plus h minus y t divided by h minus y prime t, okay, equal y double prime over 2h plus oh squared, okay. And what is this one? What is this term? So what is the question mark? It's t. It's not equal 0, okay? So it's t, yeah. So essentially it's t, right? Because y prime is just equal f, yeah. So it's yeah, it's go to 0 when h go to 0. I agree, but right now we just fix h. So what I want to say is essentially this equation, yeah. So t will be given by this form, yeah, because this is the left is just t, capital T, and this is the right hand side. So essentially we got exactly this, okay. So that is the local truncation errors. So now we go back to Euler method. So now remember we have the Euler method. What we try to prove is, yeah, that is how we define f. Remember, yes. So y prime equal f, yes. So that is the ODE, yeah. So dy over dt is just f, yeah. Okay, so now go back to the one we try to prove. So we are trying to prove the errors. Okay, so now what we are trying to prove is, so that is preparation, yeah. So we got something. At least we have 2 boxes we prepared, yeah. So now we try to prove the errors. Okay, so the errors at time tn plus 1 is defined to be, so this is the exact solution. okay, minus the numerical solution. So this is the exact solution, yeah, so exact, right? Maybe up to here, yeah, exact solution. And this is the numerical solution. So the difference between the exact and the numerical gives you the errors, right? But remember what we have for YTN plus 1. So we prepared before, right? So if you go back to, maybe let me call this one is number 1, yeah? Okay, so we prepared already. So YTN plus 1 can be expressed by these 3 terms, yeah? So I replace you know, YTN plus 1 by these 3 terms. Plus HFTN YTN minus YN plus 1. Okay, so if I replace by, you know, number 1, that I got it exactly this. Okay. But what is YN plus 1? So remember, what is Euler method? So Euler method say that, okay, YN plus 1 is, so this one is just the number 1, yeah? So from number 1, yeah? And now if you remember, yeah, we have a box for YN plus 1. No, we have a box for YTN plus 1. So this one is different. Okay, so this one is the exact value, exact solution at Tn plus 1. But this Yn plus 1 is a numerical solution. Okay, so we don't have a box for that yet, but we have a formula from Euler method. So this one can be written as Yn plus HF Tn Yn, right? So this is the this is the numerical solution. How you define Yn plus 1? Yeah. So now I put everything together. So I have the whole thing here. Tn y Tn. Okay. And now, okay, so now I rewrite a little bit. So I rewrite a little bit, yeah. So I rewrite. So I collect the terms, yeah. So this one will be YTN. Okay. And then minus Yn. So minus Yn. Okay. Yeah. Plus H of F Tn YTN. Yeah. Minus, so this is the big one, yeah. F Tn Yn. Okay. And that's it. No, maybe the last term, yeah, 1, 2, 3, 4. So 1, 2, 3, 4. The last term is this H capital T Tn. Yeah. So you see it, yeah. So now what I'm trying to do here? So if you look at the structure, yeah. So this one is on the left, it's just En plus 1, yeah. And on the right, so this one is my En, right? And this one is just f of, well, so now you remember there is, we assume that Lipschitz, yeah? So if you remember there is assumption on the function f, so we assume, well, maybe let me write down first, yeah? So h the n. Let me write down like this first, and then I apply the triangle inequality. En plus h f of En y En minus f En yn plus h En the absolute value. And if you remember the assumption on the function f, so we assume that f of t y1 minus f of t y2 doesn't go very far compared with the distance between y1 and y2, right? So this is from the assumption, yeah. If we don't have this assumption, then I mean it's not easy to prove this. So, but then I get out this. So if I can apply this assumption, then I have En plus h L, and y1 minus y2, it just become y of Tn minus yn. Yeah. Plus h Tn. Okay, but what is this one? So this one is just En, right? So this one is just the errors at the step n. So then this one is En, yeah. So then this, the whole thing is just 1 plus HL En plus H Tn. Okay, so you got something like this. So it's like a recursive relation. So it's like a recursive relation. And you see, I mean, I would use this recurrent. I mean, I use this recurrent relation to get out En plus 1, right? Because, you know, like suppose I put in n equals 0. So what is E0? So E0 is given, right? So E0 is just y at T0 minus y0. So it should equal 0, right? So E0 is given, right? And then after that, you got E1 is less than or equal 1 plus HL. So L here is just a Lipschitz constant, okay? Time E0, right? Plus H T0, right? And similarly, you got E2 is less than or equal 1 plus HL E1 plus H T0. Sorry, T1, yeah. And so on. But you see the idea, right? And then I just, you know, replace this one by 1 plus HL 1 plus HL T0, right? Plus H capital T T0 plus H T1. Yeah, and then I just sum it up. I just sum up on the terms. Okay, so that is the idea of the proof. And now, you know, I go back to the slide and you will see exactly how it works. Okay, so I go back to the slide. So you see that we got this errors, Yeah, so exactly this. And we can take epsilon to be the maximal of all the truncation errors. Yeah, so epsilon here is different from machine epsilon. Okay, so this one is just not a very good notation. Yeah, and then you start from E1, E2, E3, and so on, and then you have a geometric series. Yeah, have a geometric series. So up to En. And then, you know, I mean, there's a formula for the geometric series, so you can rewrite this in terms as this one. And if you use calculus, you can show that 1 plus x less than e to the x. Okay, so you use mean value theorem or something. Yeah. Then eventually this one is just a constant. And then what is left? So what is left is just the order h, right? So that is exactly what we are trying to prove. So we're trying to prove that the errors is bounded by this max of truncation errors. And remember the truncation errors is of order h. Yeah, so by this lemma, so order h. So therefore Euler method has order h. Okay, so that is how we prove it. So maybe we stop here for 5 minutes break, and we start again at 1:13. Yeah. So question is order h or order 1? Well, good question. So usually, you know, we say OH for order 1, right? Or OH square is for order 2. But, you know, we use it a bit like interchangeably, you know, so order 1 or order OH is the same, yeah. Okay, but essentially the power of H is important, yeah. Yes, OH square is order 2, yes, it's correct. Okay, so let me stop the recording for. Okay, so we start again, yeah. So now we prove that Euler method, the order of conversion is 1, yeah, OH. And now, yeah, so the error of Euler method is OH, yeah. So we talk about just explicit Euler method, okay. But instead of using the approximation, you know, at remember in the previous pictures, let me remind you the pictures we had before. So remember we have a pictures before of Euler method, yeah. Okay. Okay, so in this step, okay, you replace the quadrature by the integral of this rectangle, yeah. But remember, you can do another way. So suppose I have y_t1 is y0 plus h f t1y1, right? So what does it mean? It means that I take the the area of the rectangle of a bigger rectangles. Yeah. So this one is T1, right? So this one T0. So before I take a smaller rectangles, but now I can take a bigger rectangles. Then I will have what they call an implicit Euler method. So why is implicit? Well, because you got y1 on the left and y1 on the right. Yeah. So y1 is defined implicitly. So this one we call it implicit Euler method. Okay. Or you can replace, by trapezoidal rules. Yeah. So if you replace by trapezoidal rules, you have T0 here, T1 here, and the area is here. Yeah. Then you got y1 is y0 plus h over 2 f T0 y0 plus f T1 y1. Yeah, so you got the, so this one definitely is a better method, right? Because the area is approximate better than just by a rectangular rules. Yeah. But the price you have to pay is now you have y1 on the left, y1 on the right. Yeah, so implicitly defined. So this one we call it trapezoidal rules, trapezoidal method. Yeah. But now if you look at the trapezoidal method, so you see y1 on the left and y1 on the right. Yeah. So how do you solve it? How do you get y1? So how do you get y1 when you see something like this? I mean, you cannot put in MATLAB like this, right? I mean, if you put in MATLAB like this, you got y1. Yes, you have to solve it. So f solve, okay, so f solve is if you have MATLAB, but suppose before MATLAB introduce this, then you have to use other way, and one way is fixed point iteration. Yeah, fixed point iteration is easier, right? So you can define. So remember, this one is, suppose what you want is u, right? So this one is, suppose I put this one is u. Yeah, is a function g of u, right? Because what suppose I put g to be y0 plus h over 2. Okay, so what is gu? Yeah, so gu is given by this f t0 y0 plus f of t1 u, right? So essentially this one is just the y1 is just a fixed point of this equation, u equal gu. And you remember your fixed point iteration. Yeah, so if you use fixed point iteration, then you can define u0 equals something, right? So you define u0 equals something, some initial guess, and u1 is just equal g of u0, right? Okay, and now then I will, instead of writing u here, okay, so instead of writing u here, because I don't have the solution yet, I just put in u1, right? So u1 is the approximation of u. Yeah. Then I have, what is g of u0? So g of u0 is just y0. You put in 0, right? So, well, maybe I just set u0 to be y0. How about that? Yeah. Then I just got y0 plus h over 2 f of t0 y0 plus f of t1 y0. Yeah. And then I have but what is this one? So f of t0 y0 is just this one is just y0, right? So this one is just y0. So f of t1 y0. Right. F of, well, maybe just f of t0 y0. Yeah. T0 y0. Yeah. Then I can put this one into my fixed point iteration. Yeah. So I can put it in. So then I have y1 is y0 plus h over 2 f t0 y0 plus f of t1 u1. So t1 u1 with this one. Plus f of t1 y0. So essentially you can somehow approximate the unknown equation. You can approximate the unknown solution by a fixed point iteration. Okay, in this case, just one iteration. Okay, so that is the idea. And now we go back to the slide. Yeah. Okay, so the implicit Euler method. Yeah, so we discussed about that already. So like you have to put y1 on the left, y1 on the right. And if you just, like move on, then you got yn plus 1 equal yn plus h f tn plus 1 yn plus 1. So it's appears on the left and the right hand side. So implicit method. And then every step you have to solve an equation. Yeah. So we talk about trapezoidal method as well. So if you replace the area of the rectangle by the trapezoidal rules, then you got this formula, right? So yn plus 1 is now yn plus h over 2 ftn yn ftn plus 1 yn plus 1. Okay, so it's the implicit methods. And question? Good question. I believe in project. What you need is just a explicit Euler method. Yes. Okay. So in the Runge-Kutta method, then you need explicit and implicit. Okay, but we talk about later. Yeah. No problem. So now, yeah. So you see the equation can be solved by iteration. Okay. So here that like I said before, right? So if you define GU to be a function like this, then you can solve by fixed point iteration. Yeah. So remember that you have to have G prime in less than 1 in absolute value. Otherwise, you don't have a conversion. Yeah. So this one is a fixed point iteration. And when you put it in, then what you have is, okay, so now before I chose y0, u0 to be y0, so then I got different method. But if I chose u0 to be y1, okay, then we have Heun's method. So it's up to you. You can choose. You know, in this case, the initial guess is given by the explicit Euler method. Yeah. Then you have Heun's method. So just a different way to choose the iteration. And now you can see that Heun's method, you know, now is an explicit method. Okay, because on the left you have yn plus 1, but on the right everything just yn. Okay, and this one people say that is a class of predictor corrector method. So you give some initial guess, okay, you put it in, and you get out the correction. Yeah, so y1. So now if you use Heun's method, okay, so now if you run experiment before, so you can see that when h equals 0.5, you got the max errors is about 0.9. You reduce h by, well, maybe 0.5 to 0.2. You don't see it very clear, but say from 0.2 to 0.1, you can see that the errors drop from 0.01 to 0.023. Okay, so if you do a bit more, you see it drop even further. And you can guess that what is the order of conversion of Heun's method? What is your guess? What is your guess? So remember, this is Euler. Euler is this in this column, yeah, and this one is the Heun's method. You can see that the order is about OH square. Okay, the errors. I mean, you can see it numerically, right? I mean, yeah. So the order is OH square. Okay, so now we discuss about Runge-Kutta method. So Runge-Kutta method is, wow, so remember Heun's method. Heun's method, you can write down in this form. Okay. So B1 and B2 are just some constant. In this case, just 1/2, right? And C1, there's no C1, but C2 is just equal 1. And now you can write down Heun's method in this form. And now we will see why the order of conversion is order 2. So so now suppose you construct the local truncation errors again. Yeah. So remember, so this one is in a general form. Yeah. So Heun's method, but you just put on the constant is just some free constants. Yeah. And see how does it get to the order 2 conversion, OH square. So remember the local truncation errors. So this one, the first term here, is just the approximate of the derivatives. Yeah. So when h go to 0, this one just go to y prime. Okay. And when h go to 0, this one should go to. So what is this one? So what is the terms I highlight here? Well, remember this one. So this one just come from number 18 here. Yeah. So it is yn plus 1 minus yn over h Okay, so it's just a numerical derivative of the method. Okay, so the numerical derivatives, yeah, should approximate the exact derivatives. Okay, when h go to 0, when h go to 0 means that n go to infinity, right? So n go to infinity, then roughly this one is the numerical derivatives of the method, and this one is the derivatives. Yeah. So what we want to show is we want to show the local truncation errors. Yeah, can be made to be order OH square if you can choose the constant B1, B2, C2, and A21 wisely. Okay, so that is the idea. Yeah. And so how do we do that? So how do we do this? So remember, we have to use Taylor polynomials. Yeah. So if you use Taylor polynomials, then we can write out this one. Okay, so Taylor theorem. Yeah. So first, let me. So what we are trying to do. So let me try to explain. So what I'm trying to do is I'm trying to explain how we design order 2 conversion method. Okay. So this one is the method is given like this. So xi1. So xi1 is yn. Xi2 is yn plus h a21 f dn xi1. Okay. And yn plus 1 is yn plus h b1. Okay, f of dn xi1 plus b2. Yeah, so this one b1, yeah, b2 f of dn plus c2h xi2. Okay, so this is my method. So right now I don't say anything about the constants. Yeah. So A21, B1, B2, C2 are real constants. Yeah. So what I want is I want. Yeah. So this is what I want. The local truncation errors. You see in the proof of Euler method, yeah, the local truncation errors give you the order of the errors of the method. So now I want the local truncation errors, okay, to be of order OH square, okay, by choosing those constants. And what is the local truncation errors in this case? So local truncation errors in this case is yt plus h minus yt over h, okay, minus b1f dn xi1 plus b2f dn plus c2h xi2. And like, if you remember, this one is nothing but yn plus 1 minus yn over h. Yeah. Then you can see that this one is a numerical derivative, right? And this one go to y prime when h go to 0. As h go to 0, yeah. And this one should go to y prime as n go to infinity as well. So the local truncation error will go to 0. but we want to go down as order OH square. We want the errors go down OH square. So how do we do that? Well, first, remember Taylor theorem. So you use Taylor theorem everywhere in this chapter. And so what does Taylor theorem say? Well, so you got y t plus h, yeah, is y t plus y prime th plus y double prime t over 2h squared plus OH squared, right? So this one is your Taylor theorem, and you can rearrange it and divide it by h. So it just gives you y prime plus y double prime over 2h plus OH squared, right? But remember y prime is just f, right? So remember the ODE, y prime equal f. So this one is just f dy plus y double prime over 2h plus OH squared, yeah. Well, maybe let me add another term, yeah. Maybe let me add a third order derivative. Maybe I add a third order derivative here first, yeah. So y with the first, this is order 4, yeah, plus y triple prime over 3 factorial h squared. Okay, so let me correct this. So I want to add on a triple derivative 3 factorial h squared. Yeah, and now here I have a triple derivative as well. So before this term, I want a triple derivative h squared over 6, yeah, plus O 3. Okay, so I just add an extra term, yeah. And now if you remember y double prime, so we got y prime equal f, right? So we got y prime equal f th, ty, yeah. Then what is y prime? So y double prime. So y double prime is just partial respect to t of f. You take derivative respect to time on the left and on the right, yeah. Okay, and then this one will become partial f with respect to t plus partial f with respect to y and partial y with respect to t. Yeah. So this one, y prime again. So y prime, question? Some question. Let me. So how do we get a question? Yeah. Is it H4 or H3? Good point. Should be H3. H4 on the good observation. H4 is on the first line, yeah. But then here we divided by H, so it should be H3. Thank you. So it should be H3, yeah. Okay. So here we got H4 and we divided by H. This one H3. Yeah, so that's correct, yeah. Sorry about that. Yeah. Okay. So now I think it's correct now. Yeah. Okay. So now we go to this term again. Yeah. So this one will be partial f with respect to t plus partial f with respect to y time. So y prime here just equal f again, right? Right, because this is the ODE. Yeah. Then I will put it in. So I will put it in the whole sequence here. So I put in the whole sequence here. So then this one become f of dy plus 1/2. So h over 2. Then y double prime partial f with respect to t plus partial f with respect to y f. Yeah. Plus y triple prime over 6s squared plus os cubed. Okay, so I just plug it in. Yeah. So why I'm doing this? Well, because remember we have to use Taylor expansion for the second term of the local truncation. You see, so you need to some cancellation here, this second part. So that's why I want to expand it in terms of f. Okay. And now if I consider so this is the left hand side, yeah, or the right hand side. So the right hand side is, so I will put in, so f of on the right hand side, yeah. So I have, well, so b1 f of tn xi 1, not the right hand side, but the second terms of the local truncation errors, plus b2 f, f of tn plus c2h xi 2. But what is xi 2? So xi 2 is just yn plus h a21 f of t xi 1. Yeah, but xi 1 actually is yn. So maybe we just put in yn here. So this is yn. Yeah. So if you remember how we define xi 1 and xi 2. Yeah. So now this term is okay. This term is okay. Yeah, we leave it here. But this term, you see, this term can be expanded by Taylor expansion, right? So f of tn plus c2h yn plus h a21 f of t tn, yeah, tn yn, yeah, tn yn. So tn yn here can be expanded by Taylor expansion with two variables. Okay, so this one will be f at tn yn. Okay, so tn yn is this term, yeah. Okay, plus partial with respect to t. So partial f with respect to t. And so this one will be, well, partial with respect to t, right? And multiply with the difference. So the difference will be C2H. So C2H here. So C2H, yeah. And plus partial f with respect to y. Yeah. Time the difference in the y direction. So H821 f of Tn yn. Okay. And you know, some higher order terms, so I don't have to worry about higher order terms. So maybe OH square here. Okay. So now the local truncation errors. So now the local truncation errors again. So the local truncation errors again. So if you remember the local truncation errors. So local truncation errors, I think the local truncation errors, this one we should put only T, not Tn. Then we should put only T, right? Because everything is T, yeah. So we have no T. We have T, but not Tn. So T. Okay. Otherwise, it will not cancel. So on the left, T, on the right is T. So this one is only when T equal Tn. Then you got this. But in general, you just put in T. Okay. And if we go back, then so if you go back only T, yeah. So this one is only T and Y, yeah. So no index, we just put it in a general form. So you don't need a Tn here, yeah. So in some general T and some general Y. It's still correct, yeah. Otherwise, we don't have a cancellation. So no index, no index. Okay, so that's still correct. Okay. Okay, so now the local truncation errors is yt plus h minus yt over h, yeah, minus b1f t xi 1, yeah. So it will be so t so this one will be t of y, right? Okay, because xi1 is just yn, but it's just y, yeah. Minus b2 f of t plus c2h xi2, and xi2 is just y plus h a21 f of ty, yeah. And now you plug in the results from the Taylor expansion. Okay, so if I plug it in from the Taylor expansion, then I got f ty, yeah. So this one from Taylor expansion, yeah, from Taylor, you get f ty plus f ty well, h over 2, so you have to multiply by h over 2 in the beginning, plus h over 2 no, I think we have to copy down from down here, yeah. So I have to copy down from down here. So then I have so then I should have f of ty plus h over 2 partial f partial t plus partial f over y f, okay, plus y triple prime over 6h squared plus OH cubed. So this is the first term, right? And you minus the second term. So minus B1 F of Ty, yeah, minus B2, okay? And you got the Taylor's function, so F Ty plus partial F partial T C2H partial F partial Y H A21 F Dy plus y squared. Okay. So you can combine the terms. So now you can combine the terms, yeah. So what I have is 1 minus B2, sorry, 1 minus B1 minus B2 times FTY, right? And then after that, I have, so this gives me this term, and this term, right? And then after that, I have H, okay, so the term H here, so H over 2, so H over 2 is right here, yeah? And, well, maybe just H, yeah? And then the first term is 1/2 of partial F with respect to T, partial F with respect to T. Okay, and then I got H here as well. So I got B2C2, right? Time partial F with respect to T. Yeah. And now, you know, I mean, I have some higher order term. I have well, maybe not higher order term yet. I still have partial F with respect to T, right? But I still have the H, and so this one is gone, yeah. So this one is gone, and now this one is gone, yeah. But still I have H, and then I have partial F. Now I have 1/2 partial F with respect to YF for this one, and then I have A21 partial F respect to Y of F plus some higher order terms. So I don't worry. Okay, because what I want is I just want to make the lower order terms equal 0. Okay, so you see that now I just want to make the lower terms equal 0. Then I got the local truncation error just order OH square. And I can do that, right? So now I show you back the slide because the slide is clearer, but essentially the same, yeah. So the slide give you exactly the same calculation, but is a bit like skip a few steps in between. So you see that in the end, at the end of the calculation, you have order 0 term, order H here, order H here, order S square, and this one order S square. So now if I make this term equal 0, this term equal 0, this term equal 0, then I have a local truncation of OH square. So that's exactly what it is. So if you choose those constant, okay, to satisfy the 3 equations, then you have a method of order OH square. And that is exactly Heun's method. So Heun's method is just one solution. So now you have four unknowns, but you have 3 equations. So you have more freedoms. Okay, so Heun's method is just one solution. And you can define other methods as well. So if you take, you know, those parameters, then you can have your own methods of order 2. And that is the ideas of Runge-Kutta methods of order 4. So we define Runge-Kutta method of order 4 by the you know the equation like this. So you approximate by a quadrature, yeah, which has a better of approximation order than trapezoidal rules, yeah. So trapezoidal rules just give you order 2, right? But Runge-Kutta method can give you up order new for any new, yeah. So the general formula is, at first you have to set up xi1, xi2 up to xi new. Yeah, new is the number of stages. And then unify yn. I mean yn plus 1, yeah, yn plus 1 is defined to be the linear combination of f at those xi1 up to xi new. Okay, so those coefficients can be found by solving the system of nonlinear equations like we did for order 2, right? But you know, now I just write down everything in terms of the table. So the table give you the solution for second order, yeah. So this one is C1, C2, and this one A21, and this one you got B1, B2, yeah. And you know, I mean, for third order, then by the same method, then you can have those 3 equations, and then you have a solution for those 3 equations. Okay, and fourth order, so this is a third order and fourth order. So this one is the solution for those nonlinear equations for order 4. Okay, so we stop here and I let you ask question if you have question.